Transistors form the heart of almost all of the digital logic material that we've covered thus far in this course, including your computers, your smartphones, right? This is the basis of the entire digital evolution, so it would be a terrible crime for you to graduate as an engineer and not really understand how transistors work. That being said, in a mechatronics context, transistors are also often used as a way to control larger currents or voltages that you might need to control actuators in a mechatronic system. So that might be a motor, it might be a lamp, it might be a speaker, for example. So there are a lot of reasons why you might use a transistor beyond the digital logic context in a mechatronic system. Now we're going to start with trying to understand what a bipolar junction transistor, or a BJT, is. And this is formed based on a diode. So a diode, as you may remember, would have an N-type silicon region. And so that would be silicon, S-I-L-I-C-O-N, the element silicon, that's doped with something like phosphorus or arsenic, so that it has extra electrons basically floating around. And that is pressed up right next to P-type silicon. And P-type silicon would be silicon that's doped with something like boron, so that it has effectively missing electrons or holes that can be filled in. Right? That creates a PN junction that would create our normal diode. Now, to create a bipolar junction transistor, on top of this we would add another layer. So we could add a P layer, and so we could create a PNP diode. Or similarly, we could create another N layer on this side and create an NPN diode. So we would have our NPN. These are two different types of bipolar junction transistors, or the PNP bipolar junction transistor, or BJT. The symbol for each of these looks fairly similar, but there's going to be one arrow defining the difference between these two things. So I have an arrow in this direction for the NPN transistor, and for the PNP, I have an arrow in this direction. So you can see that these are three terminal devices, and the first terminal that's going to ultimately control how this transistor behaves is called the base, right? And this is the same on both of these. Right? The emitter is always the side with the arrow on it, and the collector is going to be the third terminal. And so often you'll see these written just with a B for base, a C for collector, or an E for emitter. I'm also going to define a couple currents and voltages that are going to be of interest to us. The first is going to be the base current. So that is IB, and that exists on both of these. So this is the current going into the base of this transistor. I also have, going in this direction, IC, and that's going from the collector to the emitter in the NPN transistor, and from the emitter to the collector in the PNP transistor. So both of those are IC for I collector. And then finally, I have the voltage between the base and the emitter that I'm going to define as VBE for V base emitter. On this side, the emitter is going to have the higher voltage, so I'm going to define it effectively as VEB, but the positive side is on the emitter side. But that's VBE there, and for the NPN transistor between the base and the emitter like this. And so obviously you can also define things like the collector emitter voltage, so I would have plus minus VCE right here. I can define a bunch of other voltages and currents as well, but these are going to be the primary ones that I'm concerned with. And the key point of these bipolar junction transistors is that they're effectively a current-controlled switch. So my collector current here, this IC going between the collector and the emitter, is going to be controlled by my base current and this drop between the base and the emitter, this VBE term. The other key point for my transistors in general, in this case BJTs, is that my base current can be small, and that can control a very large IC. This is effectively giving me current amplification, or current gain is another term for it, and oftentimes you'll see that written as beta or HFE. And this is key for our mechatronic systems because I might have a small current coming out of a digital logic device, something like your Arduino, and I might want that to control a large current that I'd be using to drive a load like a motor or a speaker, for example. And so in this case, this single device, right, 3-terminal device with a base, collector, and emitter, I can have a very small current going into the base, and that's controlling a much larger current going from the collector to the emitter. Okay, and if I'm thinking about these as a current-controlled switch, I want to know how to turn that switch on and off, respectively. So I'm going to create a little grid here. I'm going to create a matrix where I'm going to look at both NPN and PNP transistors, and I'm going to look at how to turn them on and off, respectively. And the key behind all of this is going to be this VBE term right here that we defined between the base and the emitter. And that's effectively a diode. Remember that an NPN transistor, bipolar junction transistor, looks like N silicon next to P silicon next to N silicon. So these are two diodes effectively. And what I'm trying to do is, if I remember what my diode curve looked like, if I plot I versus V, then I have at some point some turn-on voltage for that diode. And that turn-on voltage for a silicon-based diode is typically going to be about 0.6 volts. So this is going to be off if this term right here, this VBE term, is less than 0.6 volts. And so if that's the case, then my IB will be approximately 0 and my IC will be approximately 0. Right? It won't be exactly 0 necessarily, but it'll be pretty close. I'm effectively not getting any current gain in this device. Right? The same thing holds for the PNP transistor, but in this case, my VBE is defined from the emitter to the base. But in this case, still, I'm looking at a VBE is less than 0.6 volts, which means that my IC is approximately 0, IB is approximately 0, and my IC is approximately 0. All right, but let's get to the more interesting cases where I'm turning my switch on. So once again, turning things on are going to mean that I'm above that turn-on voltage, which basically pegs this at that turn-on voltage. So I'll have, in this case, a VBE is going to be approximately 0.6 volts from that base to the emitter for the NPN. And in this case, I'll have an IB greater than 0, and I'll have an IC, my collector current, a lot greater than 0, right? So remember, I'm getting current gain in this BJT transistor, so my collector current is going to be a lot larger than my base current. And of course, the same thing is going to happen for my PNP. In this case, my base electrode voltage is also going to be about 0.6 volts, but that's defined from the emitter to the base instead of from the base to the emitter. And in this case, once again, IB is going to be greater than 0, and my collector current is going to be a lot bigger than 0. All right, so off, effectively, I'm not getting any collector current or very small collector current, and that's because I haven't hit that turn-on voltage of this diode right here. Once I hit that turn-on voltage, then my transistor is on, and I have a very large collector current, given a small base current. Okay, but on for a transistor is not as simple as it sounds. It's not as simple as a switch where I get current or I don't get current. I'm going to have some interesting behavior when my switch is on, depending on the voltage across the collector and the emitter and the base current that I have going into the device. Okay, so I'm going to plot my collector current versus my collector emitter voltage. And so this is, I'm assuming things are on right now, so that base emitter voltage, I'm doing an NPN here, my base emitter voltage is about 0.6 volts, and my collector emitter voltage is the voltage between my collector and my emitter here. And so I'm plotting the collector current that I get versus that voltage across there. So I can kind of think of this as the voltage drop in my transistor. And I'm going to do this for several different base currents. Okay, so a small base current, I might get something that looks kind of like this. A slightly larger base current, I might get something that looks like this, and so on along here. So these curves right here are increasing base currents. Right, and hopefully right away you can see that I have a couple different behaviors in here, and I'm going to draw a kind of line of demarcation here. So above this line, if I have a larger collector emitter voltage, I'm basically getting an amplification of my collector current, of my base current to my collector current that looks like this. So that is defined as that beta term that I talked about earlier. So that beta is my current gain. And you can find this data in a transistor data sheet, and typically it might be around 50, say. So if I'm in this region, which we call the linear region, then I'm going to have a pretty defined current gain. If I shove a little more base current in, then I'll get more collector current out, right? And once again, I have a fairly large drop, or a larger drop, of voltage across my collector and my emitter. All right, if I'm down in this region, say I'm operating right here, I can have a slightly smaller base current or slightly larger base current, and they look the same, right? My collector current that I get out the end doesn't change. And so this region right here is called the saturation region. Right? And this is also defined effectively by having a small collector emitter voltage drop. And where this really comes into play is if I'm using a transistor as a switch. Instead of just a basic current amplifier, if I'm interested in using it as a switch, if I'm using something as a switch, then I typically want a very small voltage drop across that device. And so I'm going to want to be in this saturation region if I'm using my transistor as a switch. Right? To illustrate that, I have this circuit right here where I'm trying to switch the current going through a motor. I want to turn that motor on and off, for example. And so in order to do that, I want as much voltage dropped across this motor, maybe that's a lamp or something else, or a fan. I want as much voltage dropped across that motor as possible. So this voltage drop right here, which is defined as that VCE, I want to be small. So that, my total voltage drop across this circuit is going to be V motor. If I want this to be as large as possible, then I need this to be as small as possible. And a great rule of thumb to operate in that saturation region, or that small VCE region, is to have a current gain, instead of something like the 50 that I'd have in my linear region, more at 10, say. So something approximately 10 will give me a point in this saturation region, and that also gives me a VCE of approximately 0.2 volts. And if you look at a transistor data sheet, you'll see exactly why I get this 0.2 volts for this particular current gain. So if I set up my circuit to get this current gain, then I'll get this particular voltage drop, which is fairly small for a BJT transistor. Let's do a quick example using a BJT transistor to drive a motor. So in this case, my motor resistance, I'm going to say, is pretty high at 100 ohms. And in this case, I have an NPN transistor here that I'm trying to switch, right? That's going to control the collector current and ultimately the motor current, which will control the torque in the motor. And I'm interested in finding this resistance right here, right? What value of resistance right here I need to put this NPN transistor into saturation in order to switch this motor on and off effectively. I'm going to assume I'm driving this from an Arduino, so my V-in is going to be 5 volts, right? And if I'm in saturation, remember, I know that my VCE is going to be approximately 0.2 volts, and that I can use to calculate what my collector current is going to be. So I'm assuming here this VCE is approximately 0.2 volts. So if I look at V motor, and I didn't give you a definition for V motor here, let's say that's 10 volts, then my collector current is going to be V motor minus VCE over the resistance of that motor, and that gives me approximately 98 milliamps for my collector current and my motor current. So now also to be in saturation, I want an IC over my base current, or a current gain, to be approximately 10. So this means I need a base current approximately 1/10 of that collector current, or 9.8 milliamps is what I'm going to want for my base current. Now to turn the motor off, I can set Vin equal to 0 volts, say this is from a digital output pin of my Arduino, then my VBE will be less than 0.6 volts, and in that case, right, the whole transistor is switched off, and my collector current is approximately 0. But if I assume that Vin is 5 volts when I want the motor on, then I can calculate my base current as the input voltage minus that diode drop between my base and my emitter over this resistance right here. I want this whole thing to be equal to this 9.8 milliamps up here, and that is ultimately going to give me that I want an R of approximately 450 ohms. All right, so if I used a much larger resistance right there, right, that would actually push me into the linear region of my transistor curve, right? And then this would have a much larger voltage drop across here, which could affect how I'm driving my motor. But if I use a resistance of 450 ohms right here, then I put this transistor into the saturation region, which automatically pegs this collector emitter voltage for around 0.2 volts, right? It's not exactly 0.2 volts, but somewhere around 0.2 volts. And gives me a current gain then of about 10. And that allows me to reasonably efficiently switch my motor, right? If I have a smaller voltage drop across here, also this makes a better switch because it's more efficient. I have less heat or power dissipation in the transistor as well. So this gives you one example of how I can use a transistor, a BJT transistor in particular, to switch a larger load in a mechatronic system like a motor.